This video is on enthalpies of formation. So an enthalpy of formation is shown with the symbol of delta H with the subscript F and then the degree sign. The enthalpy of formation is the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard state. So we'll talk about what that means. So important things to note is this is for 1 mole. 1 mole of a substance. And I'm making my substance from the elements, and my elements are in their standard states. So if I were to make water, the two elements that make up water are hydrogen and oxygen. It's important to note that I want to make 1 mole of my product. And to make a balanced equation for 1 mole of my product, I need to have the 1/2 in front of my oxygen to just give me 1 oxygen. And I need a 1 in front of my hydrogen because it's a diatomic and I have 2 here. So to make this balanced, to show my 1 mole of product, I'll also note that my hydrogen and my oxygen here are in their standard state. So this means that the amount of energy required for this reaction is actually a release of energy. So when the hydrogen and the oxygen combine, they release 242 kilojoules per mole of heat energy. And it's important that we have this per mole, which is why we have 1 mole of product being made. So standard states for elements are going to be their form at 1 atmosphere and 25 degrees Celsius. Pure substances are going to be a liquid or solid at room temperature. So those that are liquid and solid at room temperature, their standard state is the substance at 25 degrees Celsius, because remember that pressure doesn't influence our liquids and solids. And then for gases, their pure substance is going to be what they are at 1 atmosphere of pressure, because we can remember that pressure has a big influence on gases. Solutions, their standard state is their concentration at 1 molar. Okay. In your textbook, there's Appendix 4 at the back, and this lists all of the enthalpies of formation for a whole bunch of compounds. It lists the 2 elements that come together and then their formations there. So you can check out Appendix 4 in your book. It's important to note that when we're calculating my standard enthalpy of formation, it's just an extension of Hess's law. So we look at formations and kind of unformations, so the breaking down and the making of my compounds. So to figure this out, an enthalpy of formation, I can summarize that my total enthalpy of formation is equal to the sum of my products, where N is the molar coefficient attached to them, and subtracting from that, so minus the moles times the heat of formation of the reactants. So difference in heat between the enthalpy of my reactants and my products, just like we said above. It's that change in enthalpy. So if I were to look at my example, methane, when combusted with oxygen, is going to make carbon dioxide and water. So it's a standard combustion reaction. If I were to start looking up in my textbook, I would find out that to make methane's made from carbons and hydrogens, and oxygen is in its standard state already. So since it's in a standard state, its enthalpy of formation is 0. So it's really important to note that this is 0. When I look up in the back of the book, I would find that for methane, the formation of methane would be negative 75 kilojoules per mole. But because my methane is being broken down, right, I'm taking it apart to make my carbon dioxide, I need it to be a reactant. That's why I have it listed here as positive 75. So there's a couple of ways you could go about this. One way is where you can look up your enthalpies of formation for all of your molecules. So we're going to do that first. So in the back of the book, when I look it up, I find that to make methane, I have a delta H of negative 75 kilojoules per mole. To make oxygen, that has a delta H of 0 kilojoules per mole, because that comes from its elemental form, and it is its elemental form, so there's no change. To make carbon dioxide, that has a change in enthalpy of negative 393.5 kilojoules per mole. And to make water, that has a standard enthalpy of formation of negative 242 kilojoules per mole. So if I look at my reaction, I see that I have my methane and my oxygen as reactants. So that means that instead of making them, I'm breaking them down. So these are going in the opposite direction, which means I need to change the sign on my enthalpy of formation. So that becomes positive. I also have to take into account my molar coefficients. On oxygen, we have a 2 in front of it, so I have to multiply my heat of formation by 2, which in this case doesn't matter because it's 0. Carbon dioxide is a product, and my enthalpy of formation is of being a product, so this stays the same. And then water, we see that water has a 2 in front of it, so I need a 2 here, which means I multiply my standard enthalpy of formation of water by 2, because this is per mole, and I have 2 moles. Doing this, I can add them up. And when I do that, adding these, I get total standard enthalpy of formation of 802 kilojoules. The other way that I can do this is I can use my formula here, which is where I don't have to look at if it's being made or broken down. So in this case, my heat of my reaction is equal to my molar coefficient of my products times the heat of formation of my products minus the sum of the molar coefficient of my reactants times their individual heat of reactants. So my products being my carbon dioxide, my water, I have 1 in front of my carbon dioxide, and to make carbon dioxide, it's negative 393, plus my other product of water, I have a molar coefficient of 2, so 2 times my amount of energy for my water, which is negative 242, minus my reactants, so my methane, which was negative 75, and 1 times negative 75, plus my oxygen, which has a molar coefficient of 2, and oxygen is 0. So when I do this and I add these all up, I get 802 kilojoules. So it really doesn't matter if you go about it this way, which is just like how we were doing things in Hess's law problems, or if you use our enthalpy change of reaction formula and add and subtract and find the difference between them. You're going to get the same answer. It's just preference on how you go about doing it.